Hi everyone, this is the video from section 4.4 on operations with complex numbers. We talked about in class about the idea of what an imaginary number is, and those are the numbers that are the square roots of negative, the square roots of negative values. And we did some work with those, and we're going to broaden this a little bit and move into the idea of what a complex number is. So I want you to, as normal, go through and take notes on this and write down any questions that you may have as we go through the problems together and the rules together. But we're going to start off by defining a complex number. And a complex number is a number that contains both a real part and an imaginary part. The form that it fits is this form a plus bi, where a is going to be the real part and the bi is going to be the imaginary part. So it's important that you understand the definition of what a complex number is. An example that you could put into your notebook would be something like this, 5 plus 3i. That's an example of a complex number. The 5 in this is considered to be the real part because it doesn't have the I associated with it. And the 3i is the imaginary part. And together, those two pieces form what we consider to be overall a complex number. Now, any complex number where the a value is equal to 0 is considered to be a pure imaginary number. And those are the kinds of numbers that we were working with earlier in the section that we did together in class. So the pure imaginary numbers are the values where we have a 0 in this spot here. Instead of having a real number there, we have 0, which would just leave us with the imaginary part. And if you only have the imaginary part, that's considered to be a pure imaginary number. So strictly definition on this page, make sure that you write down any questions that you might have, though, about the ideas of what a complex number consists of, and ask me when I see you next time in class. So moving on to the next page. This would tend to make sense. I think it's pretty much common sense as we go through this rule, but we'll talk about it a little bit. Two complex numbers are considered to be equal if and only if, that's the IFF, their real parts are equal and their imaginary parts are equal. So we've got to make sure the real parts are equal, and we've got to make sure that the imaginary parts are equal. So on the screen, I have two complex numbers. The first number is a plus bi, and the second is c plus di. The a and the c are considered to be the real parts of these complex numbers. And in order to be equal, a would have to be equal to c, and b would have to be equal to d. So to put two complex numbers equal to each other, we've got to make sure that we match up the a and the c and the b and the d. In the problem below here, we're going to look at forcing two complex numbers to be equal to each other. So this example asks us to find the values of x and y that make the complex numbers that we have here true. So the first complex number is this number, 3x minus 5 plus y minus 3i, and the second complex number is 7 plus 6i. So the biggest thing in order to tackle a problem like this is to figure out what the real part is and what the imaginary part is. And those two pieces need to be set equal to each other. So the imaginary part is always the piece that's right in front of the I. The real part is everything else. So in this problem, the 3x minus 5 is the real part of this complex number, and the 7 is the real part of the second complex number. These two have to be equal to each other in order to make the two complex numbers equal to each other. So 3x minus 5 has to equal 7, 3x will equal 12, and x will be equal to 4. To make sure that the entire complex number is equal to the other complex number, the two imaginary pieces have to be equal to each other as well. So the i's we know are going to stay, and what comes before the i's have to also be equal to each other. So I'm going to say that y minus 3 has to equal 6, and y will be equal to 9. So in order for these two complex numbers to be equal to each other, the value of x has to equal 4, and the value of y has to be equal to 9. You're going to see some problems like this as we work a little bit more together with these in class when I see you next time. So again, write down any questions that you might have about the definition of setting two complex numbers equal to each other, and then in the problem where we actually solved for the variables to make the numbers equal. Pretty quick and easy bit of information here. When we work with complex numbers, all of the basic properties that we had for real numbers, like the associative property, addition and subtraction properties, commutative properties, all those types of properties hold true for complex numbers as well. So the next 4 examples actually just look at some of the basic properties that we used in the real number system and just translate them over to the complex number system. So the first, all the directions are going to say to simplify. The first example says, please take the complex number 5 minus 7i and add to it the complex number 2 plus 4i. So this is our operation in the middle. Now to work with complex numbers, when we add and subtract, you can only combine like terms, just like we did with the real number system and when we worked with variables. So real can only get combined with real, and imaginary can only get combined with imaginary. So in the end here, we can combine the 5 and the 2 and get 7. Those are the 2 real parts. And negative 7i plus 4i is negative 3i. That's the combination of the imaginary parts. So 5 minus 7i plus 2 plus 4i is equal to 7 minus 3i. Not rocket science. The second example is asking us to subtract 2 complex numbers. 4 minus 8i is the first complex number, and we want to subtract 3 minus 6i from that. Now, same as with the real number system, when we subtract, we have to make sure that we change signs. So this really turns into 4 minus 3, which is 1, and then negative 8i plus 6i, because we have the minus the negative, which will be minus 2i. So the difference of these 2 complex numbers turns out to be 1 minus 2i. Again, not too difficult. The only place that I'm going to catch someone with a problem like this would be that they're forgetting to change, and distribute the negative sign through in order to change the signs there. As far as multiplication goes, complex numbers basically look like binomials. So when we're asked to multiply 2 complex numbers together that have both real and imaginary parts, we use the approach just like we did with real numbers and binomials, and use the FOIL approach. So when we work with multiplying the complex number 3 plus 5i multiplied by 2 minus 4i, we're going to use that same approach. So we get 6 minus 12i plus 10i minus 20i squared. Now, in all of these problems, you're going to have some more simplifying that you can do. We're going to look to combine like terms. We're going to look to simplify powers of I that we know can be simplified further. So we're going to get 6 minus 2i, because these are like terms here. And then we know that I squared is equal to negative 1. So because the I squared is equal to negative 1, and we're multiplying that by the minus 20 or the negative 20, this turns into a plus 20. So we end up, we end up with plus 20 there. So our final answer is going to be 26 minus 2i. And if you really want to dazzle me, you could do this. Factor out a GCF of 2, and that will leave us with 13 minus I. So final good simplified answer would be 2 times the quantity of 13 minus I when we multiply those 2 complex numbers together. The last one is another multiplication problem, and it reads the complex number 4 minus 6i being multiplied by the complex number 4 plus 6i. If I go through the FOIL process here, I get 16 plus 24i minus 24i minus 36i squared. Now, looks similar to what we did above. Here, these 2 middle terms drop out, and then this is going to become positive 36. So we end up with 16 plus 36, or 52 in the end. This is the product of two complex numbers that actually multiply together to give you only a real number. Kind of unique, and we're going to talk about that on the next slide. So the way that I can easily tell that I know that the whole FOIL process doesn't need to be used here, where I multiply this all out, is the fact that each of these has the same real part, has the same imaginary part, but the signs in the middle are opposites. So if you see that situation, it's almost like a difference of two squares situation. If I multiplied x plus 9 times x minus 9, I know I get x squared minus 81. I don't get any middle term once I would work with the FOIL idea. So if you can see that, it'll give you a little bit of a shortcut, and you won't have to do as much work. So basic addition, subtraction, multiplication operations going on there. I think I missed my circle. Not too challenging, but always room for silly errors, which I know some of you make. So just think before you work. Those two complex numbers that we just talked about in part D, the 4 plus 6i and the 4 minus 6i, are called complex conjugates of each other because of the setup that they have. They have the same real part, they have the same imaginary part, but they have opposite signs in the middle. That will always, always, always result in a real number. So keeping this rule in mind is going to be helpful as we go through some of the problems that are going to involve the division approach. So knowing that we could form complex conjugates and knowing that complex conjugates always multiply together to give us just a real number, that there's no imaginary part to the number, is going to be helpful in the future here in the next couple examples. So I think I have 4 more examples to do. These two ask us to simplify, and now we're switching over to division. We did an addition, we did a subtraction, we did 2 multiplication, and now we're going to do a bunch of division problems. And the simplification of division problems is a little bit more time consuming. You have to put a little bit more thought into things. If I look at this problem, remember I stands for a square root, really. This represents the square root of -1. And you should have learned way back when in algebra that you can never leave a radical in the denominator. Leaving radicals in the denominator are not good presentation form in math. So this form, 4 plus I over 5i, actually can't be reduced at all. We can't divide the i's out because we can't divide out across addition. The only thing that's wrong with it is the fact that we technically, even though it doesn't show right on the board, we have a square root in the denominator. So we need to get rid of that square root. If I had given you, we'll do a side problem over here, 3 plus, no, let's do this. If I gave you 3 over radical 6, I'm hoping that you would recognize the fact that this form isn't good and that we need to rationalize by multiplying by radical 6 over radical 6 to get the radical out of the denominator. So your final answer would be 3 radical 6 over 6, which would then reduce to radical 6 over 2. So we're not allowed, remember, to leave radicals in the denominator. This is an example of a concrete real number approach to things that you've done in the past. Now we're going to translate this idea over to the complex number system and working with imaginary numbers. When we have a situation like this, this is really telling us we have 5 times the square root of -1 in the denominator. So to get that radical out of the denominator, I need to multiply the numerator and denominator by the radical that's in the denominator. So since it's not presented in the radical form and it's really in the 4 plus I over 5i form, I'm multiplying by I over I. That's the equivalent of multiplying by the square root of -1 over the square root of -1. And when I do that, this I in the numerator gets distributed through. So we have 4i plus I squared over 5i squared. We need to make any simplifications that we can. I squared, remember, is -1. So this becomes -1. This becomes multiplied by -1. So our final look will be 4i minus 1 over negative 5. Now, if we could reduce, we would reduce. If we could factor things, we would factor things. But in this situation, we're going to leave it exactly as is. You may see in your book answers that look like this, the negative 5 being split up into each term in the numerator. So negative 4/5 I plus 1/5 is another acceptable form of this answer. And we can talk about that translation in class if you're confused about how that would come about. I'm perfectly fine with you leaving your answer just like this. Not a problem in my eyes. So in the second problem, 5 plus I over 2I, what's standing in our way here of having proper form is the I in that denominator. So I'm going to multiply by I over I. I don't care about the coefficient. The 2 can stay there. That's perfectly fine. That's not a kind of an illegal presentation. When we multiply by I over I, we get 5I plus I squared over 2I squared, which is going to give us 5I minus 1, since this I squared is negative 1, over negative 2, since this I squared is negative 1, and we're multiplying. So acceptable answer for me. Your book, again, may show this as negative 5/2 I plus 1/2. So either of those two forms would be fine with me. We may need to have a little bit more of a conversation about this when I see you in class, if there's any confusion about this. But basically, we're simplifying by getting the radical out of the denominator. Now, the last two problems that I have for you are along the same lines, except for the denominator is a little bit more complex. And I say complex because there's an actual complex number in the denominator. It's not just the imaginary piece of the complex number. It's not a pure imaginary number. So when we have a complex number in the denominator, the way that we're going to quote unquote get rid of the radical that exists there is not just by multiplying by I over I. We need to actually multiply by the entire conjugate of the denominator. So that means I'm going to multiply by 3 minus 6I over 3 minus 6I. And I know by doing that, I'm going to bring a real number into the denominator because we just learned that multiplying two complex conjugates together always yields a real number. In the numerator, I'm going to distribute the 2I across. So that gives us 6I minus 12I squared over, and because I know that these are complex conjugates now, I only need to multiply the first and the last. That gives me 9 minus 36I. I'm going to simplify the I, 36I squared. I'm going to simplify the I squareds. So this is 6I plus 12 over, this becomes plus 36. So 9 plus 36 is 45. And I'm going to inspect this a little bit further. We tend to like the real part written first. So I'm going to switch things around, but then I'm going to also look to see if I can simplify by reducing it all. I noticed that in the numerator, 6 is common as a GCF, so I'm going to pull that out and I get 2 plus I left. The denominator 45 is going to stay as is, but now what I notice is 6/45 can get reduced. 3 goes into each of those, so I'm going to have 2 times the quantity of 2 plus I over 15. And that's going to be my final simplified answer. So what I need you to do here is not only get the radical out of the denominator by multiplying through by the complex conjugate, but I need you to look to factor and reduce your answers to be simplified as much as possible in these situations. In the second problem, 2 plus I over 1 minus I, the complex conjugate of that denominator is 1 plus I. So I multiply by 1 plus I over 1 plus I. This is the equivalent of 1, so it's not changing the meaning of the problem, it's just changing the look of the problem. The numerator this time is actually a binomial times a binomial, so I need to FOIL this. 2 plus 2I plus I is going to give me 3I in the middle. Excuse me. I multiplied those together and added together. Plus I squared over because the denominators are complex conjugates of each other, we just do the first and the last to get 1 minus I squared. This I squared is going to turn to -1. This I squared will turn to -1 as well. So we're going to get 2 minus 1 is 1 plus 3I over 1 minus -1, which is 2. I'm going to inspect what I have here. It's in real plus complex or real plus imaginary form in the numerator. There's no GCF, that can't be factored. The denominator is a real number. There's no more I in that denominator. So this final form is 1 plus 3I over 2. So that's all I have for examples for you. Within the section, or the end of the section, because this wasn't the entire section, we covered the basic operations with complex numbers, what a complex number actually is, and then how to work with addition, subtraction, multiplication, and division involving complex numbers. So, you know, review the video if you didn't get something, write down any questions that you might have, and then we can talk about them together in class before you begin a problem set with these types of problems. Thanks for listening, and I'll see you next time in class.